dimension of this moduli space, you would have to incorporate an Euler characteristic and dimension term, which gets a little bit annoying if you want to talk about kind of like a zero-dimensional moduli space. And so the idea is that by using this weird shifted grading, it takes care of that for us, and you can write the virtual dimension as just the index at the top minus the sum of the indices at the bottom. Okay, anyways. So that's why there's this weird shifted grading that appears. And then I also wanted to make sure that I computed cylindrical contact homology in one example so that you felt like we did something. So for the irrational ellipsoid, here u and v are complex numbers. So I can take norm u squared over a plus norm v squared over b and set that equal to 1. A and b are going to be positive, and then I want a divided by b to be irrational. In that case, I just have two embedded closed Rabe orbits. One I'll call gamma 1, which lives in the u equals 0 plane. Gamma 2 lives in the v equals 0 plane. If you use here, you use the contact form I over 2 u du bar minus u bar du plus v dv bar minus v bar dv. If you write down what the Rabe vector field is, you'll have to have like a times the u stuff and then a b times the v stuff, so that when you plug it in, you get like norm u squared over, you know, whatever. You get norm u squared plus norm v squared equals 1. So you need kind of like the a and the b there to make sure you get the right answer. And then that a and the b kind of corresponds to rotation by a in the u plane and rotation by b in the v plane. And so if a over b is irrational, then you're not going to be able to go from the u plane and close up in the v plane. So you just end up with two embedded Rabe orbits. Michael works it out in his Taub's proof of the Weinstein conjecture paper very nicely. And then the Conley-Zander index formula for phi 1, that's a over b. For phi 2, it's b over a. And then the Conley-Zander index of gamma to the k is going to be k times 1 plus phi I. So this is your like theta that appeared before. And so in particular, this is always an integer. You multiply by 2, you always get something even. Then you add 1, so you get something that's odd. And so because your generators of your chain complex always have odd Conley-Zander index, that means that there can be no differential between them. And so your chain complex is just the homology. So you have a Q, because we have to do this weird shifting, which is plus n, which would be 2 minus 3, so you'd subtract 1. So I have like an odd number that would start at 3 minus 1, will give me 2, and then I get all the other odd degrees. It's I don't know, an exercise to check that you only get one. That with this formula, each Conley-Zander index number appears only once, and they're always odd. And so you get a Q in every even degree that's greater than or equal to 2. And if you kind of had all the invariants in the world and stuff, you could use this kind of this expression for what the homology groups are to say that this illustrates that there have to be either exactly 2 Rabe orbits for S3 or infinitely many, where you would get exactly 2 embedded Rabe orbits for S3 when the differential vanishes, and you get infinitely many, which would correspond to the differential non-vanishing. So your homology expression usually is kind of infinite, and the appearance of like the Q's kind of is supposed to tell you where kind of the embedded Rabe orbits have to be, and you can also try to construct capacities, which kind of tell you about the minimal action for your Rabe orbits. But the kind of nice thing about this theory is that it should be pretty easy to compute, whereas sort of symplectic homology and the non-equivariant contact homology tend to have sort of twice as many Rabe orbits, and the differential is a lot more complicated. So this theory kind of has a lot of transversality and compactness issues, but it is kind of easy to compute. So that's supposed to be its like saving grace. Okay. So the dream of Eliashberg, Giventhal, and Hofer was that this sort of construction worked. assume there are no contractible Rabe orbits of grading -1, 0, or 1, and this grading is this weird shifted Conley-Taylor index. So here in dimension 3, you have grading of gamma is CZ of gamma -1, and so this ellipsoid example satisfies those hypotheses because the sort of first grading shows up in degree 2. Okay. But this is an assumption that you need even if you have all the transversality in the world, which I'll hopefully get to in a little bit. Okay, then this should be associated to a closed, non-degenerate contact manifold. Let J be a generic lambda compatible structure. Then the differential is well defined. Well, the differential means that you can either take kappa delta or delta kappa. D squared is equal to 0, and the homology of this chain complex is actually an invariant of the kernel of lambda, meaning it doesn't depend on the choice of lambda or the choice of J. Okay, so before, I guess, continuing, I'll say a few words about sort of positive results. So in 2014, Hutchings and I proved that in 3 dimensions, if CZ of gamma contractible is always greater than or equal to 3, which is called dynamically convex, basically, then we prove that delta kappa delta is equal to 0, so e.g. D is well defined, and D squared is equal to 0. But we didn't get invariance, so invariance is more complicated. So this is a paper that we just posted in June for no contractible Rabe orbits, and then we have to do some obstruction bundle gluing, so we'll have a paper in 2020 if there exists contractible Rabe orbits. Okay, this is like 30 pages of math, and this is like 150 pages of math, and this will be like another 100 pages of math, but we get some other things too. Then, let's see, Bao and Honda have a paper from, I think, 2015 or 2016. So they prove this in the, they get a contact invariance, which you can show by the filtrations that Michael and I established in our 2019 paper, which is isomorphic to cylindrical contact homology, which is a contact invariant in the hypertight 3-dimensional setting, which is in the absence of contractible Rabe orbits. And then Pardon has a paper, I think, from 2018, let's say, And this is invariance via Kurenishi structures if there are no contractible orbits in any dimension. Okay, so sort of, we're kind of, a lot of our hope is in low dimensions. I guess the nice thing about the paper that Michael and I just put up on the archive is that we get a substitute for cylindrical contact homology in any dimension. We also get a non-equivariant counterpoint which captures more information. Those are well defined, and then we can relate them back to this original theory of Eli-Ashberg, Giventhal, Hofer. So I'll talk more about that next week. But I just kind of wanted to say that this is, achieving this dream is still kind of an active area of research. Okay. So before I get into sort of what the difficulties are, meaning sort of the compactness and transversality difficulties, this expression for the differential is a little bit mysterious, and you see these multiplicities appear, and it's not too bad to sort of explain the proof of why delta kappa delta is 0, which shows that you really have to sort of encode the multiplicity of the ray orbit at some point. So I'll do that, and then after that I'll tell you a little bit about some of the compactness and transversality issues. So if you want a reference for basically what I'll do for kind of the rest of the time, this is the 2014 paper by Michael and I, and this is 1407.2898. The reference. Okay, so the idea is that if we pretend that compactness works the same way as in Morse theory, meaning that an index difference 2 holomorphic curve can only, if we had a sequence of index difference 2 curves, that it could only limit, it's only sort of breaking, it could only break once into 2 index difference 1 pieces. So suppose we knew a sequence UK of index difference 2 cylinders could only limit to a once broken cylinder. So here's our like UKs, and then they limit on a once broken cylinder. So this is kind of our starting assumption. Then we can prove the following lemma. Suppose J is generic. This is in the HN14 paper, and this is for dimension 3. And this assumption that Conley danger index of gamma contractible is greater than or equal to 3. But sort of this lemma is true in dimension 3, but you would need an analog of this lemma to be true in arbitrary dimension to kind of get the differential to square to 0. But we can only sort of prove it in dimension 3 because we can only prove this, that a sequence can limit in this way, assuming dimension 3 and assuming this dynamically convex assumption about the grading on the contractible ray orbits. Okay, so suppose J is generic. We have U plus in some moduli space J gamma plus gamma 0 mod R. So it's an index difference 1 curve, so I'll denote the index of U plus as this subscript on M tilde, and I'm modding out by R, so that's the M, but it gets confusing when you have like index and virtual dimension running around, so this is really to say that the index of U plus is equal to 1. Okay, and then I have U minus is in M1, and then we've got gamma 0, gamma minus mod R, so here's my gamma plus, here's my gamma minus, and then it's breaking sort of along gamma 0. And we also assume that gamma plus minus are good. And then for simplicity, we write k is equal to the greatest common divisor of the multiplicity of u plus and the multiplicity of u minus. So this lemma is going to be kind of like the key result that you need for gluing. And no one ever has time to explain gluing in a summer school. But basically what happens is when you're trying to show that d squared is 0, you want to sort of count the ends of the compact one-dimensional manifold. So the way that you do that is you have some sort of compactness argument or you have some sort of understanding of what the compactification of a moduli space of pseudo-holomorphic curves look like, which tells you that so compactness, this will tell you that if you compactify this space from gamma plus to gamma minus, it will live in the disjoint union over all sort of gamma knots where you do and you want this to be the boundary. So the boundary of this compactified moduli space is it just consists of once broken curves. This is becoming microscopic. Okay, so compactness. Okay, so compactness tells you that if you have some sequence of elements in this moduli space, that they can limit to some sort of broken curve. So that tells you that if you look at the boundary of the compactified moduli space, which would include all these limit curves, that you're going to be somehow contained in the space of once broken curves. But in order to prove that d squared is 0, you need to have equality. So the way that you get equality is to prove the reverse inclusion, which is a gluing argument. Okay, and what is a gluing argument? So a gluing argument is a way of using one word to describe many hundreds of pages of functional analysis. That sounds convincing. Because, oh yeah, I glue two cylinders together, of course that's what happens. So what you're doing is you have some cylinder here, and you have some cylinder here. So that's my u plus and my u minus. And then using bump functions, you can turn that into sort of a pre-glued curve, but it's not sort of honestly J holomorphic. It's just got two bump functions, and on one half you know that u plus is J holomorphic, on the other half u minus is J holomorphic. Then you turn your functional analysis crank, you have to look at some formal adjoint, show that it's bounded, and you can say that nearby there has to be an honest solution to the d-bar equation. Therefore, near every pre-glued curve there is an honest glued curve, which is your unique pseudo-holomorphic solution. But in the case of cylinders where we have multiply covered curves, the sort of pre-glued, or the honest J-holomorphic solution is not unique. There's actually a whole bunch of them, which depends on the multiplicities of the curves and stuff. But the gluing argument is running the opposite of compactness, so that you can actually say that the boundary of this compactified moduli space is exactly once broken curves. So the sort of best reference for gluing is going to be Odan and Damian's book. They've got several hundred pages about gluing, but they've got a nice, overview chapter that tells you all the functional analysis that goes into it. If you read Dietmar's Fluor theory notes, it just says, a standard argument shows blah. And you're like, okay, great. What does that mean? And then you discover, as an adult, that means that Dietmar is good at analysis. And it's not a judgment on you. Okay, anyways. So I just wanted to say, gluing is a thing, but no one ever says anything about it, so I wanted to say 3 words about it. Okay, anyways, so this is kind of the key gluing result, but it's not going to look like a key gluing result, but it is. And the statement is that then A, there are K m of gamma naught divided by m of u plus m of u minus ends of the moduli space of index difference 2 curves that go between gamma plus and gamma minus that converge to this building. So this is precisely sort of the gluing statement where you're going with the opposite inclusion. And B, each such end consists of cylinders of multiplicity k. Okay, so normally in Hamiltonian Floer theory, or even in Morse theory, or in symplectic homology, you only have somewhere injective cylinders, and all of your orbits are just time 1 periodic, and so you never see like multiplicities appear, you never see ends having multiplicity, you just see that there is like a unique solution that corresponds to the ends of the moduli space. So here, because we have these multiply covered curves running around, I'll show you kind of some pictures. I want to illustrate the proof of this lemma, because this is how you prove, this is what ends up showing you that delta kappa delta is 0. But basically what's happening is that you have all these different parametrizations, because when you do your gluing, you're working in a functional analytic framework, so you have to pick parametrizations of all your curves. But you're going to have sort of a certain number of parametrizations which are all the same, which has some action given by multiplicities of curves and cylinders and stuff. And so then in order to not end up having sort of like overcounting of your ends, you have to divide and multiply by things. And you don't end up with a unique number, you don't end up with a unique solution because of these like multiplicities that are running around. But of course, if all of your curves were somewhere injective, this m would be 1, this m would be 1. If all of your orbits were just time 1 periodic, this m would be 1. And the greatest common divisor of 1 and 1 would be 1, and then this would just look like the standard sort of thing in Hamiltonian Floer theory. And then the way that you can say that delta kappa delta is going to be 0 is because you'll see, so delta kappa delta, this is going to be m of gamma 0, then you'll have an m of u plus and an m of u minus. You have some coherent orientation stuff. Okay, great. And then the point is that if you know that there are this many n's and they each have multiplicity k, then and you're looking at a compact one-dimensional manifold, and then you count those n's with sign, then you're going to end up this is going to be equal to 0. Okay. But we definitely don't have time to talk about signs, but sort of the reason why this m of gamma 0, m of u plus, m of u minus is so important is because it's exactly the delta kappa delta, which is exactly this m of gamma naught divided by mu plus mu minus, and then the multiplicity k of the n's divides by this multiplicity k, and then you count with signs and everything's fine. Okay, anyways, so why is this lemma true? Okay, so at the space of solutions, so this means that we do not mod out by the automorphism group of R cross S1. we will have m of gamma naught divided by m of u plus u minus distinct parameterizations of curves in M twiddle J. So phi plus corresponds to u plus, phi minus corresponds to u minus. And because we're working with parameterizations and we want to keep track of them, we're going to specify an initial point condition. So we have limit as s goes to minus plus infinity, so you have the minus and plus reversed, of the projection of y of your parameterization of s0 equal to some initial point p. So here is phi plus. So we want a base point constraint on the bottom. So this line, this is phi plus of s comma 0. So projection to y is going to give me a point on gamma 0. And then if I look at phi minus of s0, if I look at the positive end, I want that point to be the same. And because I'm going to glue these two cylinders together, if I want them to match up, I need the initial point on gamma naught to be the same initial point of my parameterizations. And then the point is that I have these distinct parameterizations because once I look at my cylinder, if I have multiplicities running around, then I can just kind of rotate by that portion of an S1 action, and it'll be the same. It'll be a different parameterization because I didn't mod out by this S1, but once I mod out by S1, then it will give me the same curve in M twiddle J. Okay, so here. So here's, let's say, my U plus. Here's my U minus. So I have some distinguished point P that I want to glue together along gamma naught. And let's say that the multiplicity of gamma naught is equal to 4. So that means that my gamma naught is not embedded, but there's going to be some underlying thing that's 1/4 times the length, and so in theory I could just rotate this by z mod 4, and I should end up with the same curve in M twiddle. But now let's say I want to make life even more awful, and let's say that my orbit down here, so this is gamma minus, is has twofold symmetry. And I mean, we can just leave, we could make this M of gamma plus be equal to 1. So it just has one-fold symmetry. So then the multiplicity of U plus would be equal to 1, whereas the multiplicity of U minus would be equal to 2. And so then for the top curve, there would just be, there would be 4 distinct parameterizations, because I could either have taken this to be my P, this to be my P, this to be my P, or this to be my P, so I have that rotation. Whereas for this bottom curve, I only have 2 distinct parameterizations because from like, oh, I guess I should have drawn it like this. So this is like gamma minus is some curve that's doubly covered, and then I've tried to unwind it. So the point is that from here to here is going from here to here, which is going to be the same as like going from here to here. So I would only have 4 divided by 2 distinct parameterizations, phi minus. And so things get a little bit complicated because there can be, 4 distinct parameterizations for U plus, but only 2 distinct parameterizations for U minus. And then if I make a pre-glued curve, how many different curves should it correspond to inside of M gamma plus gamma minus? And the claim is that you just run this formula, which just corresponds to understanding how group actions work of a circle, which is, you can give yourself quite the headache thinking about it. Okay. Great. Okay, so the point is that these distinct parametrizations that we have for gamma, for phi plus and phi minus, which are the things that we're going to construct a pre-glued curve out of, this gives m of gamma naught squared divided by m of u plus m of u minus distinct pairs, phi plus phi minus, satisfying this point constraint on the middle ray orbits. We know that they can be sort of glued together at the end of the day. Okay. But we've somehow like this maybe should not be distinct. This just gives this many pairs, satisfying star. And then the question is, we have this number of pairs, but now we want to know if we pass to m twiddle j, sort of how many like u plus u minuses does this correspond to? Okay, so the cyclic group, so we look at the cyclic group corresponding to the multiplicity of gamma naught. So the cyclic group Z mod m of gamma naught acts on the pairs phi plus phi minus by rotating the S1 coordinate, and two pairs glue if and only if they lie in the same orbit. Where glue means you run this functional analytic crank, which means that you get a sort of holomorphic curve corresponding to sticking phi plus and phi minus together with a bump function, and you'll get some honest pseudo-holomorphic curve that's arbitrarily close to the broken one. So then each orbit of this Z mod M of the breaking orbit action has cardinality m of gamma naught over k. So the number of orbits is the number of pairs, which is this m of gamma naught squared divided by m of u plus m of u minus, divided by the cardinality of the action. And that's exactly the k of m of gamma naught divided by m of u plus m of u minus n's. And then the k is coming from the fact that you're looking at the greatest common divisor of this guy with this guy, which is exactly sort of when you glue these curves together. If this thing is only once multiply covered, this thing is twice multiply covered, when you glue it together, the multiplicity of gamma plus will still be 1, the multiplicity of gamma minus will be 2, and so you're stuck. You're just going to have a somewhere injective curve, even if you glue, like if you glue one somewhere injective curve to a not somewhere injective curve, your resulting curve will be somewhere injective, and so you're just taking the sort of greatest common divisor to figure out what the honest pseudo-holomorphic curve in M2, what the multiplicity of that guy is, which is this k, which is the greatest common divisor. Okay, great. Okay, so, I don't know. Takes like, it's just kind of weird that you are doing this. You have to like kind of keep track of an S1 orbit if you sit down and read gluing one day, you'll understand. Otherwise, I don't know, you can just forget this ever happened to you. Okay, so at the end of the day, the upshot is that you have to have weighted differentials in order to get that d squared is 0 in cylindrical contact homology. That corresponds to some kind of complicated functional analysis stuff that I'm not really saying much about, and because there are so many different parameterizations. So the upshot is that multiply covered curves just kind of make you have to think a lot harder about life. And if this gluing argument was the worst thing that we had to worry about, then life would be a lot better, but unfortunately it's not. But at least we kind of have an idea of why we have a weighted differential and what is involved in gluing. Okay, so I guess before I go into compactness and transversality fun, are there any questions? Okay. And I guess, well, I won't make any promises about what Vinny has to say, but in embedded contact homology, the differential is kind of even more complicated, and the gluing that you have to do is more complicated because with your pre-glued curve, you'll have a U plus and a U minus, but then it turns out that you have to put in a bunch of branched covers of trivial cylinders at this level. And in order to understand how to count that, it's not going to be just some mumbo jumbo about algebra that you forgot. You have to do something called obstruction bundle gluing.
Don't scare people.
But Vinny's not going to do obstruction bundle gluing. But I had this picture here. In ECH, you have like all these extra things that you have to glue in, and it gets complicated. Okay, anyways. And these like pictures, I don't know, it's really ridiculous. Like I said, in ECH, deep, go here. But that's 200 pages of math by Cliff Taubes and Hutchings, which are dedicated to Deusa McDuff on the occasion of her 60th birthday. So that should tell you something, which is maybe that symplectic geometers are crazy. Okay, anyways. Okay, so part 3. Okay, so if you are in a, I don't know, if you do end up with an advisor that makes you do some stuff with counting J-holomorphic curves and symplectizations or exact symplectic cobordisms or stable Hamiltonian structures, you're going to have to learn some things about compactness and transversality. And unfortunately, Chris Wendell taught a course which whenever he teaches, he turns his like actual lecture notes into typed lecture notes, which like turn into books, which is a skill I have yet to master. But he has lectures on symplectic field theory, which are, I think, like 300 pages at this point. But they're probably kind of the most comprehensive notes if you want to learn about pseudo-holomorphic curves and symplectizations, which are not showing up in ECH. If they're showing up in ECH, then you want to read Michael Hutchings' lecture notes on embedded contact homology. But if you're doing other things, Wendell has some nice kind of lecture notes. And so there's sort of two like issues in constructing, or maybe not constructing, but in understanding, let's say, moduli spaces of pseudo-holomorphic curves. Are going to be compactness and transversality. So transversality is kind of, like everyone eventually just gets that transversality refers to wanting to run an implicit function theorem type argument to say that my moduli space is cut out transversely. Therefore, it has the structure of a manifold or maybe an orbifold. And that's great because once you have this structure, then you know that the virtual dimension is sort of bounded below by whatever the space of automorphisms exists in your target. And so then you know that all the curves for generic J have to have, index at least 1 or something in a symplectization, or index at least 0 in an exact symplectic cobordism. And that gets you a lot. And, having that a zero, you're counting elements of a zero-dimensional moduli space, which is compact. That gets you that the differential is well-defined. And sort of compactness and transversality together is what's going to get you that d squared is 0, and you need these both together in order to get the chain map, or to get the chain homotopy, or the homotopy of homotopies. So I don't really want to talk too much about transversality. There's lots of details in Wendell's book. Compactness, I'll say sort of a few words about. So compactness, this comes from a paper by Bourgeois, Eliashberg, Hofer, Vysotsky, and Zander from 2003, which is like covered in these pictures of pants and pants with holes in them and punctures on pants, and it gets like pretty awful. And the sort of upshot of this paper is that a moduli space of what are called asymptotically cylindrical J holomorphic curves in a symplectization, and you can also generalize this to be a stable Hamiltonian structure, or maybe it's just a cobordism, but anyways. And asymptotically cylindrical means that we have sort of cylindrical coordinates for Rabe orbits at the punctures of the domain. So my cylinder, I can think of that as a punctured S2, and then I've had that the limit of the projection went to plus minus infinity, and limit of the other projection went to Rabe orbits. Once you start to have more than sort of one positive and one negative end, then you have to introduce cylindrical coordinates on each of your puncture and say that there's some convergence and it all makes sense. That's called asymptotically cylindrical, which is equivalent to the curves having finite Hofer energy. Okay, so you can look at these moduli spaces of J holomorphic curves, and you have arbitrary genus. They just have to have limits on Rabe orbits in this symplectization, or something called a stable Hamiltonian structure. So it has a compactification. But we may not like it. Okay. And when I say we may not like it, I mean that an index difference to cylinder, if you have some sequence, this could limit onto something that's non-cylindrical. If you cap off all the other ends by holomorphic planes. Okay. Okay, and this is sort of bad for us because if we want to show that d squared is 0, we want to run an argument that's analogous to Moore's theory, and that's not going to work. And sort of what happens is that when you have a failure of both compactness and transversality, you can't assume that the virtual dimension of each of these pieces is at least 1 if you're in a symplectization. And to make matters worse, you have trivial cylinders inside of symplectizations. They exist. You can't perturb them away. And so that means that this could be a branched cover of a trivial cylinder. This could be a branch cover of a trivial cylinder. This could be a trivial cylinder. Okay, so if this has virtual dimension 0, this is virtual dimension 0, this is virtual dimension 0, then adding to 2 can be a lot more interesting when things are allowed to be negative or 0. So the only way to add to 2 is 1 plus 1. If you use positive numbers, which is what you would want to be able to do to say that an index difference 2 cylinder can only limit onto a once broken cylinder, because then each of the components can only have index 1. And the point is that sort of each of these planes, by that assumption about the grading, each has to have index 2. So as long as you can kind of rule out gross things with a bunch of negative ends from having sufficiently low index, then you would be okay and be able to say, well, it can only limit onto once broken cylinders, but life is not sort of always that nice. So the issue, so I don't know what to say exactly, but so okay. What I'm trying to say is that there's a long paper, which is maybe better explained in Wendell's notes, and it says that our moduli spaces of curves they admit some compactification, but it can consist of sort of branch covers of trivial cylinders, and then for that reason, we're not going to be able to sort of run arguments like existed in Morse theory, and so you kind of need transversality and compactness at the same time, and this has been like the struggle of symplectic geometers for the last like 25 years. And then people try to introduce sort of virtual methods, but then it becomes harder to actually count things, and I don't know, life gets hard. So maybe what I'll say is that, so the good news is that in dimension 3, and if Conley-Zander of gamma contractible is always greater than or equal to 3, what Hutchings and I proved in our 2014 paper in a symplectization, the only buildings of index 2 are a cylinder where the index difference is 2, a once broken cylinder where each guy has index difference 1, and then a branched cover of a trivial cylinder over an elliptic Rabe orbit where this has index 2 because it's a holomorphic plane, and then this has index 0, and this has index 0. Okay, so in higher dimensions, these arguments break down, so I just want to say that this heavily relies on how nice the Conley-Zander index is in dimension 3, meaning those explicit formulas that I wrote down, and we also use sort of Riemann-Hurwitz to get bounds on sort of what the index of these branch covers of somewhere injective curves can be. And then the sort of, I don't know, then there's some intersection theory. Trick, which says that an index difference 2 curve, if you have some sequence of them, that this cannot limit onto this building of this third type. So this is gamma d, this is gamma d minus 1. So this uses positivity of intersections, and by sort of excluding this third, by saying that if you have a sequence of index difference 2 cylinders, it can't break into this configuration, then that means that we can sort of run compactness the way that we want to, as it appeared in sort of Morse theory and Hamiltonian flare theory. And the other thing, I guess, that we used here, also in R cross M, you have that the index of a cylinder, which is multiply covered, is always greater than or equal to the index of the underlying cover. So the underlying cylinder, and if it's non-trivial, then it has to be greater than or equal to 0. Sorry, strictly greater than 0. Okay, anyways. So all of this breaks down once you work in a cobordism, even this nice sort of index relation about cylinders. And so next week I'll talk a little bit more about what you can do, which involves using domain-dependent almost complex structures. But that kind of breaks a lot of the symmetry so the naive arguments don't go through. Oh, right. And then, sorry, I forgot that there was one more piece. So the third piece is automatic transversality, and this only works in dimension 4. And what this says, I'll just write it down, which maybe it's like a nice thing that shows up. It basically says that if you look at, so given a J holomorphic map from a Riemann surface with a number of punctures taken away. So you can look at the genus of this domain. If twice the genus of U minus 2 plus the number of orbits with even Conley-Zander index is less than the Fredholm index of U, then U is regular, meaning that the moduli space is going to be cut out transversely. So if you decipher what this means in terms of cylinders and the fact that all of our multiply covered cylinders have to have index at least 1 if they're a cover of a non-trivial cylinder, you can get regularity for all your multiply covered cylinders and symplectizations. So I just wanted to say a few things about sort of what goes wrong, which is compactness and sort of a lack of transversality together. And so overcoming these issues usually mean sitting down and really understanding Riemann-Horowitz as it shows up in the Fredholm index and then the Conley-Zander index under iteration, which you can do in dimension 3. And then you have to sort of consider what's going on with cylinders in order to show that sort of multiply covered cylinders of positive Fredholm index are cut out transversely. You need something called automatic transversality, which I think Chris might give a talk about in a more general context next week. That sometimes you can sort of, if you have a nice, if sort of the index of your curve is big enough in terms of some topological information, you can actually guarantee that your curve is regular. So, yeah. So these homology theories, we give like 1 or 2 hours of lectures about them, and they seem very straightforward and easy to understand, but usually we're hiding a lot of details in the background. So I don't know exactly what to say, but as a graduate student, I struggled a lot because I was like, but they made it look so easy. They explained everything in 3 hours. Why is d squared equal to 0? It's okay if it takes you a while to figure that out, and sometimes you can get a thesis just by understanding when d squared is 0. So I'll end here.